are the Arduino Farm team, and we're presenting our senior design project. It is an autonomous system that manages climate, lights, and nutrients, and for an indoor greenhouse. This is our team.
I'm Genevieve. I'm a mechanical engineer on the project, and I've been primarily working on the auger and the nutrient mixing system.
I'm Karina. I'm a mechanical engineer on the system, and I've been working on the pumping and the structure for the system.
I'm Anthony. I'm an electrical engineer. I've been working on designing the climate control system and integrating the rest of the control systems.
Hi, I'm Max. I'm an electrical engineer on the project, and I've been doing the lighting and the Arduino control.
Hello, my name is Logan. I am an electrical engineer on the project, and I've been working on the sensing and controls for the nutrients and pump.
We are a first-year team. We're loosely based on a project that was started by sophomores last year. The motivation was to have a higher quality, freshly sourced produce year-round that will require less resources to grow.
For the structure, our team decided to go with a nutrient flow technique hydroponic system. This means that the nutrient-dense water is pumped through trays of plants. The seeds are planted in rock wool cubes and placed in these trays, which soak up water and keep the roots moist. I designed a structure that clamps onto that frame and holds the grow trays at an angle, so that the water then is pumped to the top trays and flows with the help of gravity down to the trays beneath, so that all plants receive water with only having to pump to the top trays. The tools and skills involved in this process are 3D modeling, fluid dynamics to calculate the optimum angles and flow through the trays, and structural and strength analysis.
My task here has largely just been modifying the panel to retain the manual control while also allowing it to have an Arduino-based option, which is the main selling point of the project. So it just has a dimmer switch here, just manual. But it can also switch over to Arduino-based control, just done by the PWM outputs on the Arduino. Very easy to implement in software, and trivial to have a communication network either serially or is based on the digital input-output pins to be controlled by a master Arduino. All 5 channels can work for each row independently. The board itself, it's a multi-layer design beginning with a rectifier, then an amplifier, all the way out to output stereo plugs with a little bit of surge protectors in there.
Within the nutrient distribution and mixing systems, there are 2 main components, the auger and the paddle. The auger is controlled by a stepper motor, which is attached to the auger connected by a coupler. The auger spins out about 1 teaspoon of nutrient each rotation. The paddle is also controlled by a stepper motor and spins at a low RPM to keep the water agitated and aerated at all times. The auger was designed using SolidWorks and Creo and printed out using the Prusa MK3S using PETG and PLA material. One of the largest takeaways from the system was learning to adapt and adjust manufacturing, including the size of the auger and how to connect.
The pumping of the system uses relays controlled by the central Arduino. An external clock has been paired with the Arduino, so everything remains running at the same time intervals, even in the case of data overflows or power outages. The nutrient sensing and distribution is a little more complicated. The nutrients are measured by a pH sensor and an electrical conductivity sensor. The electrical conductivity sensor works by emitting a small signal through the water. However, this will disrupt the pH sensor's readings. To combat this, the sensors will be attached at opposite sides of the water tank. This allows the sensors to stay calibrated and on for the entire time. The sensors feed back into the central Arduino, which drives the motor on the auger. This, however, does not provide enough current to convert into power for the precision or torque necessary. This is achieved by a small secondary power converter.
The climate system for the greenhouse is a combination of sensors and actuators running in parallel. The climate is measured using a temperature sensor, a CO2 sensor, and a humidity sensor. A heater will be activated if the temperature sensor reads too low. The ventilation fans are always running to constantly provide the plants with fresh air, but will be turned to a higher setting if the temperature, CO2, or humidity sensors read too high. If the humidity sensor reads too low, it will activate the humidifier in the greenhouse to add more moisture to the air. On the processing side, sensor readings that fall out of the designated range trigger an alarm state that calls the control subsystems to take corrective action. All of these controls are designed to autonomously create the optimal growing environment for the plants.